In this video, I'm going to show you how to solve a two-body problem on an inclined plane. So here's a fairly typical incline on the left side with an angle defined θ1 and a mass m1 on it. And then to make the problem interesting, there's a second incline on the right, θ2, mass m2. We're told the ramps are frictionless, and we're told that the densities of the blocks are comparable to each other, the same actually as each other, which kind of gives us a clue that maybe m1 is more massive than m2 since it's drawn bigger. And that makes me guess that the acceleration is that way, but again, that's just a guess because I don't really know. I don't have angle values, so it's possible that θ2 is so steep that the lighter mass m2 is still able to pull m1 up its less steep ramp. The point I want to make is it doesn't matter. You choose a direction for the acceleration and you stick with it. And as long as you do that, if you chose wrongly, that's okay, because at the end, when you plug in numbers and calculate A, you'll get a negative answer, which just means the acceleration is opposite what you expected, but it's not incorrect. What you can't do is decide halfway through the problem to switch the direction of the acceleration, say when you diagram one block versus the other, or actually more importantly, when you start comparing forces in certain directions to accelerations using Newton's second law. What I mean by that is, once you decide that this block accelerates this way, make that the positive direction and have all forces in that direction be positive, and therefore the acceleration in that direction is positive. Therefore, any forces that point up this way would carry negative signs, and similarly for this block, this would be its positive direction and this would be its negative direction, like that. So we'll stick to that. All right, having said that, let's zoom in a bit, and I'm going to make a force diagram for each mass, and it's an incline problem, so the coordinate systems are rotated. We've been here before. So starting with our forces on block M1, I have a force this way, which is a normal force, Fn. I have here a force of gravity, Fg. I have a force of tension, Ft, like that. Similar for here, Fg, maybe Fg2 and Fg1, so that I differentiate, or rather distinguish them from each other. That's Fn2, Fn1, like so, and tension. But if you saw my previous video on two-body problems, you know that in fact the tensions are equal to each other. It's the same, I shouldn't say it's the same force, because it's not the same force. They're two different forces that act on two different masses, but the magnitude of that force is the same in both cases. So that's useful information for a little while from now. Okay. We're on an incline, so I have to break the force of gravity up into components because I'm choosing to work in a coordinate system that looks like this. And the reason I'm doing that is simple enough. I'm doing it because I know that if this block accelerates, either block accelerates, it will do so in a direction that's parallel with the ramp. It'll accelerate along the ramp. It's not going to suddenly leap off the ramp and fall through it. And so therefore I want to keep one axis lined up with the acceleration. I don't want to wind up with a situation where the acceleration is like in between my axes, because then I have components of acceleration. And it's customary when doing simple Newtonian dynamics for as long as possible to keep the components of things, the sines and the cosines, on this side of the equation and not on this side. So it's preferable to try to construct the coordinate system so that your acceleration is only in the x direction or only in the y direction. Now, you can do it otherwise, but it's longer, the math is a little bit more complicated, and to be honest, sometimes it's unavoidable. But in a problem such as this, it's easy enough for us to rotate the coordinates and keep the acceleration of the blocks along the x-axis. So that means we're going to have to break up the force of gravity into two components, one of them perpendicular to the ramp, and one of them parallel with the ramp. And then similarly over here, perpendicular and parallel. This angle is θ1, this angle is θ2, and you can prove that with laws for similar triangles or other geometric ideas, but it's not very difficult to show that, and so I'll take that for now as a fact. And what that simply means is that I can write this as m1g times the sine of θ1, and this can be written as m1g times the cosine of θ1. And then similarly over here, this one is m1g sine theta. Nope, it's m2g. Rewind. m2g sine θ2. And then this one up here is m2g cosine θ2. Nice and messy. All right. So now let's write some equations. For the block on the left, M1, in the y direction, we know that the net force is equal to 0. We know it doesn't accelerate this way, up and down like that, perpendicular to the ramp. So we know that Fn1 minus m1g sine theta 1 equals 0, which is a roundabout way of just kind of coming to the conclusion that Fn1 equals m1g sine theta 1, okay? And I'll kind of put a blue box around that. A fairly obvious conclusion that I think you could have drawn just by looking at the problem, but I caution you against ever just jumping to the conclusion that the normal force is equal to anything without first going through the steps of setting up some type of equation, be it equilibrium with a 0 here or an MA. In this problem, they are equal, but I could imagine a situation where there was maybe another force pushing here, maybe this is an applied force from somebody's hand or something like that. And then, you'd have to add in a y component of that into this equation, which would make the normal force not just equal to m1g sine. What I mean is not that. So sorry for the mistake. What I mean is this. If you were wondering why I was writing that, then you're right. This should actually be Fn1 minus m1g cosine theta equals 0. There we go. Cosine theta 1 equals 0. Or Fn1 equals m1g cosine theta 1. So, my mistake. And of course, it's this force and this force that we're talking about. So I'll put a box around that. Sorry. But as I was saying, don't be so sure that this is always the case, because with an additional force here, we might find ourselves with another component to factor in. Also, I can think of situations where there actually is an acceleration. It's partly in this direction, such as instead of having a block on an incline, this might be the back view of a car. Here are its wheels, driving around a banked curve and sort of heading off in this direction, rounding a turn like that. A racetrack, in which case it would be accelerating centripetally with an acceleration a in that direction. In that case, you wouldn't rotate your coordinate system. You'd keep x horizontal and you'd keep y vertical, because now the acceleration is horizontal. And actually, the normal force would not be mg cosine theta. It would be something significantly larger than mg cosine theta. However, in this problem, we don't need to consider those things, okay? So I will eliminate that. Eliminate the applied extra force like so. Similarly, for the other mass on the other side, and I'm not going to make a mistake this time, so I'm just going to go right to it. Fn2 is equal to m2g cosine theta 2, and that becomes my y equation for that block. Okay. Nice. Now, x directions. So choosing again the downward direction down the ramp for M1 is positive, I write net force is MA in the x direction. I now write m1g sine theta 1 minus ft equals m1a. Awesome. And then for the other block in the x direction, same thing, net force is MA. I write, and I do not write that. Actually, the positive direction now is up the ramp for that block, so I would choose to write ft minus m2g sine theta 2 equals m2a. And I've got my two equations with two unknowns. The unknowns are a and ft. The other masses, and the m1s and the m2s and the theta 1s and the theta 2s, would be given. They're not really considered unknowns. At least they're easily measured. Okay, so now it's time to solve the system. Easiest way to do it is to probably just write the equations on top of each other in linear combination style. So ft minus m2g sine theta 2 equals m2a, and then this equation comes down here, and rearrange it a bit, so put the ft's on top of each other, plus m1g sine theta 1 equals m1a. Add them up. The ft's cancel, I wind up with m2g, or actually, let's write it this way. Let's go m1g sine theta 1 minus m2g sine theta 2 equals m1 plus, remember we're adding equations, m1 plus m2 times a, which makes a whole lot of sense because what I've got here is the net external force on the system. Neglecting the internal tension force, right? That's the net external force. And then what I've got here is total mass, m1 plus m2. So if you think about it as a system, you probably could get to this result much quicker than by doing all the individual diagrams with the equations, but I like it that way, so I've done it that way. And now finding the acceleration is as simple as just dividing the left side by the m1 plus the m2 term over here. So we are essentially done with that. If you want, you can factor a g out from the left side and write it a little more succinctly, but you don't have to. At any rate, the acceleration ends up being m1 sine theta 1 minus m2 sine theta 2, all times g, over m1 plus m2. And you should recognize that if, in fact, you kind of push things to the extreme, and by that I mean if you made the angles theta 1 and theta 2 both 90, then the sine of 90 is 1. So this equation would revert to one that you probably already know. For a typical Atwood machine, not with blocks on an incline, but just hanging off of a pulley, we know that A equals m1 minus m2 times g over m1 plus m2, which if you've taken basic physics is something you've probably seen before, and that's what this equation reduces to if the theta 1 and the theta 2 are both 90 degrees, so that helps us to understand that probably this is correct. It fits the pattern of something that's applicable in a more limited case if we let the theta 1 and the theta 2 take on extreme values. And often in physics, it's a nice way to check your answer, to just say to yourself, well, gee, what would happen if I let theta 1 or theta 2 equal 90, or theta 1 or theta 2 equals 0? You know, in which case you can see that you would also wind up with an acceleration of 0. It gives us confidence that this equation models reality because it works in the extremes. All right, so that's that. Now, for part B, I believe you're just asked to determine what the acceleration of the system actually is in this case. So let me just scroll up, if I still can. I may not be able to. Okay, so I'm going to handle that in just a moment. But this satisfies answer A and gives us the actual, this satisfies answer A for this problem and gives us the actual value or the expression for the acceleration. For part B, we just plug in some numbers for m1 theta 1 and m2 theta 2, so on and so forth, and we get an answer. And so now we're asked to determine the actual acceleration for both blocks, and we're given masses and angles in this case. So this is really just a matter of plugging in. Now we know we have the equation A equals m1 sine theta 1 minus m2 sine theta 2 all times g over m1 plus m2. Okay, so we take the numbers and we plug them in, and this is exceedingly simple. So 12 times the sine of 20, 12 sine 20 minus 8 sine 30. That all gets multiplied by g, which we'll take to be 10, and then adding the masses together, 8 plus 12, or 20 in the denominator. Okay, so we have to solve that. So if you calculate this, it comes out to an exceedingly small acceleration of 0.005 meters per second, which makes me suspect that even with a tiny little bit of friction on the incline, these blocks might not even move. They're almost in equilibrium even as is, which is the next topic. So for the next part of the problem, the students are allowed to add a sticky material to the incline on the left, but not on the right. So you're supposed to determine the coefficient of static friction between this material and the bottom surface of the block that would keep the system in equilibrium. So let's draw that block again. This is now the block on the left. So here's the ramp, the incline, as it's called. Here's the block, 12 kilograms. Force of gravity, M1G. Force tension, Ft. Force normal, Fn. Additional force of friction, FF. And I should say that we know it's this way because for the last problem, when we determined the actual acceleration, which we assumed was in this direction, we actually got a positive answer, which means that in fact the acceleration, if it were truly a frictionless system, would be in this direction. And so if we let the system go, it would tend to go in this direction. We were right when we chose that as the direction of the acceleration because we didn't get a negative answer, so we were right. And that means the force of friction points up the incline as I've drawn here. That's significant, okay? Now, the other block's still here. It has no added friction, so its forces haven't changed. We can use the diagram that I used a while ago, 10 minutes ago or so, whenever it was, to analyze it then. So we're looking for, remember, the minimum coefficient of friction that would keep this at rest. Minimum static coefficient of friction. Anything higher would also work. So the way I would approach this again would just simply be to write down Newton's second law. This is now in the x direction, but with the understanding that we're looking for the net force to equal 0. So this block does not accelerate, and the same also on the other block. So I'm going to write m1g sine theta 1 minus ft minus the force of friction has to equal 0 for this block. And that can be further written as m1g sine theta 1 ft minus mu times the normal force, which we learned a long time ago was, interestingly enough, equal to m1g cosine theta. That's from before. We never used it before, but we're using it now. That all adds up to 0. For the other block, I still have, this is now this block, I still have the equation m2g, or rather ft minus m2g equals, instead of in this case ma, it's also 0. Both blocks are in equilibrium. And I made a mistake, sorry. It's not m2g, it's m2g sine theta 2 equals 0. So that's cool, because now what I can do is solve this one for ft. Make ft equal to m2g sine theta 2. And that is to say, if this block is not accelerating, then the tension up the incline, ft, needs to be numerically equal to the component of gravity down the incline, which we learned was m2g sine theta 2. Like that. So they are equal because the block, only because the block isn't accelerating. So I can take that and I can stick it in there. And then scrolling down here, and I realize I'm not really answering part D yet, but I'm still on part C, so we'll cross that off. Right? But I get the equation m1g sine theta 1 minus this thing over here, m2g sine theta 2 minus mu m1g cos theta must equal 0. Again, this makes a lot of sense, since what we're saying is the net external force on the system, that's this thing, the whole outside force, net external force, gravity on one block, gravity on the other block, and then the friction on one block needs to be equal to 0. So now we just plug in numbers and solve. And if we do, we find out an appropriate value for mu. But I'm not going to do that just yet. Instead, I want to talk about what this would look like if we looked at part D. So this is part C. Let me try again. So I'll put a box around it, and put part C, with the understanding that if you actually want the answer for mu, find the minimum mu that you need, you just have to plug in numbers. We have m1, we have theta 1, it's all known, okay? But if we wanted to do it for D, D says, well, let's do the same thing, but this time let's make the other block, m2, be the one with friction. And if we did that, then the equations change a bit, right? Now, the equation for m1 would look like this: mg sine theta 1 minus ft equals 0. But the equation for the other one, block 2, would be like this. It would be ft minus m2g sine theta 2 minus the force of friction equals 0. And again, that's because now, on the incline, we've switched which block has friction. M1 no longer has it, but M2 does. And since M2 is trying to move up the ramp, the friction will be down the ramp, or opposite its direction of motion, in the same direction as this force of gravity. All right, look at that for a minute. Then, of course, we can simplify that. Minus mu, this is m2g cosine theta 2, and that's all equal to 0. So if we solve, I would suggest solving this one for ft, and we find out that ft equals m1g sine theta 1. Okay, we'll take that, put a box around it. Let's plug that in for this ft. Scroll down the page a bit. We have some room. And so this whole thing, this whole expression becomes m1g sine theta 1 minus m2g sine theta 2, looks familiar, minus mu m2g cosine theta 2 equals 0, all equals 0. Again, plugging in numbers which are given. M2 is 8, M1 is 12, and the thetas are given as well. You would be able to solve this for mu in each case. And what you'll find is that the mu that you get from in part C is different than the mu you get in part D. And that reflects the fact that in the one case, the mu friction is teaming up there with block M1, but in the other case, it pertains to block M2. So of course these mu values are going to be different because the equations are different, but notice they only differ in this one term here. Otherwise they're the same. It's just which mass has the mu with it. Okay, so of course for part E, if you read the question, of course the answers to part D and E are not the same. How could they be? Because these two equations are different. They differ by what mass is located in this spot or here in this spot. Okay, and the actual values for mu I'm not too concerned with. It's easy enough to plug in numbers for M1, theta 1, M2, theta 2, and solve for mu in each case. All right, that concludes this problem. Stay tuned for more.